Hello, everyone. Welcome to the OpenFOAM and Combustion Simulation webinar. So today we are very happy to have Professor Peng Zhang here to deliver the very interesting presentation about collective behaviors of flickering, buoyant, diffusion flames. So before the presentation, please allow me to first introduce Professor Zhang. Professor Peng Zhang joined the City University of Hong Kong as associate professor in 2022. Before that, he was an assistant and then associate professor at the Hong Kong Polytechnic University during 2012 and 2022. He received a PhD degree in mechanical and aerospace engineering from Princeton University in 2010, and then worked as a combustion energy research fellow at Princeton University from 2010 to 2012. Professor Zhang's current research areas are droplet and spray dynamics, theoretical and computational combustion, and theoretical chemical kinetics. Professor Zhang has published more than 90 journal papers in these areas. Okay, so now I give the time to Professor Zhang. Okay, thank you very much.
Thank you. First of all, I would like to thank Professor Zhang Huangwei for the invitation. It's a pleasure to be here to give a talk, which in this wonderful webinar. I'm not an expert of computational combustion, and I did some OpenFOAM simulation, but that's not topic for today. So this is something I need to apologize for everybody. So let me start my talk. First, I would like to give some introduction, and then gradually I will present to you what we found in the recent few years on this interesting topic. So back 4 or 5 years ago, at that time, I knew nothing about the flickering flames. So the reason I was got into this area is because at that time, one of my PhD students was struggling with stabilizing inverse diffusion flame in our laboratory. So we were quite frustrated because no matter how hard we try, we always found small lambda flames oscillate all the time. So then we recognized that this is an intrinsic feature of a certain lambda flame in a certain range of flame parameters. So then after we recognized this kind of phenomena, we found this is quite an interesting flame because compared with the well-known steady flame, and this is unsteady flame, and then it contains more nonlinear behavior compared with the steady flame, but it's also much simpler than turbulent flames. So if we study this flickering flame, we can study it with well-controlled ways to introduce some new features. This is the way I'm going to present this work in the following 40 or 50 minutes. So basically, we will treat the flickering flame is a flame oscillator. So since it's an oscillator, then the first natural question is ask what's the frequency of this flame. So it turned out people already observed this kind of flame long time ago, and then did a lot of experiment. So you can see on this figure, there's a lot of experimental data, and then those people try to fit those data in this scaling law with the exponent minus 0.49. This, of course, this is a funny exponent because any combustion theoretist will recognize that this probably is minus a half. So then you can see that 1 year later, and then this citizens represent all this data and then express everything in this scaling law. The frequency is proportional to the the d to the minus half. D is the size of the flame. Of course, they try a lot of different flames with liquid fuel, gas fuel, even solid fuel. So if we look at the problem from the point of view of a dimension analysis, right away you will know that if of course this is just way we understand things. Now we know this problem is buoyancy controlled because this is a very small flame. So if at that time people know it's buoyancy controlled, and then actually this scaling law is the only possibility to get this kind of scaling relation. So of course, if you look at this experiment, you will find that those experiments were conducted by using very different flames, including the pool flame and the jet flame and all kind of the diffusion flames. So the question is, can we establish a unified scaling theory to include all this data? So I think the definite step made in understanding the controlling mechanism of a flickering flame was made by the Peng and all at the 22nd symposium, combustion symposium. They show these wonderful pictures with a lot of flow details. So you can see that basically there are two types of the toroidal vortices. One is the outer one induced by buoyancy, and then the inner ones induced by the inlet jet velocities. So it's the outer, the toroidal buoyancy induced vortex and caused this the flame flickering. If you look at the right-hand side here, I show some simulation. You can see when there's a flame and then there's a vortex sheet, and then under the buoyancy, the vortex sheet will grow and then to form the toroidal vortex, or we call it the vortex ring. And this vortex ring will deform the flame, try to lag to the flame. So at a certain point, and the toroidal vortex shed off, and then to stretch the flame to form the combustible pocket of gases, and then this pocket of gases will be burned out in the downstream. So then the flame will repeat what I just said, then to form a periodic motion. So the understanding is that this is intrinsically a vortex dynamic problem, and then now we know that combustion plays a minor or secondary role in this problem. So in case my audience are not familiar with vortex ring, I just show you some figures. It's vortex rings everywhere. You can see in many phenomena in nature. So as long as we can suddenly or quickly push a flow out of a circular orifice, and then due to the intrinsic Kelvin-Helmholtz instability due to the discontinuity of velocity, there's unstable waves. The unstable waves will grow and then to roll up the interface and finally form the vortex ring. So even the dolphin knows how to make a vortex ring. So based on this understanding, right away at the time, about 4 or 5 years ago, we decided to establish a vortex dynamics-based theory to explain everything. Although at that time we already knew some wonderful work based on global linear instability. So, but actually, I did this kind of linear instability analysis when I was a student, but I was never a fan of instability analysis because too much mathematics to cover the physics. So we try to directly handle to deal with vortex. So that we start from the vorticity transport equations. So you know that the left-hand side is acceleration. It's the convective, the material derivative of vorticity, and then the right-hand side are the source terms. So you can see that the first term is due to the stretch and the tilting, and then if the flow is axisymmetric, this term is 0. And then this term is 0 because we deal with incompressible flow. And then this is a baroclinic terms due to the the gradient of density and the pressure. And then this is a diffusion term, and this is a buoyancy term. So since we don't have these two terms, and then since there's only one flame here, so we don't need to worry about diffusion. And then so this baroclinic term is essentially just a convection term. So we assume this flow is buoyancy dominated. So we only need to keep this one term. So basically you can think this is assumption that we are dealing with buoyancy dominated flow. Then rest of the derivation is quite simple. So we just use, everybody can see in your textbook of fluid mechanics or combustion control volume analysis. But here the control volume is the dynamically changing control volume, which include our vortex in this control volume. So we just do the integration of this equation in this control volume, and then we can calculate what's the vorticity or circulation inside this control volume. And then we just apply a general, very universal criteria. Fluid mechanics guys discovered this a long time ago, that for quite wide range of flow phenomena, and then the toroidal vortex will shed off from the main flow as long as its circulation reach a limit. So this limit only slightly change with flow parameters. You can basically check this is a universal constant, C. So then we just apply what we calculate the total circulation of a toroidal vortex equals to this universal constant C. And then we can solve the frequency in this way. Here we include the where along the square root of G over D here, and then with the correction due to the jet, due to the Flood number. Okay, so we include the possibility of the inlet flow velocity. So if Flood number goes to 0, then we recover the original scaling law, and then if for the jet flame, and then we can find that the Stockholm number, which is the non-dimensional frequency, can be expressed this way. It turns out our theory agrees extremely well with all this experimental data published in literature, including poor and jet flames. And so you can see this is how we present this in dimensional form, and this is a non-dimensional form. So you can see in terms of Flood number, this is a small Flood number, this is a large Flood number. So even the Flood number goes to order 1, the agreement is still very good. So basically this is the understanding of this flickering flames. So since this seminar is about computational combustion, so in the following half an hour, I will just focus on computational work. So we simulate a single flickering flame first. Okay. Then the interesting things, our understanding wasn't that good at the beginning. So because at that time we found that a lot of people observe this flickering flame phenomena by using a candle or liquid pool. So at that time, we thought maybe the liquid pool it's an important issue or factors in this kind of problem. So I asked my student to try to find the software, open source code, which allow us to study diffusion flame from liquid pool. So we found the FDS, the fire dynamic simulator developed by NIST. Probably my audience are the expert in OpenFOAM, and probably you have a lot of criticism on the resolution or the modeling of FDS. But at that time, we just try to quickly simulate something and then help us to get some flow details. So then we adopted this software. So you can see this is the just a box, computational domain, and then the field is unhapting, it's liquid phase, and then we have a nozzle here, it's a solid wall, okay, and then all the 6 boundaries of the domains are open boundary condition, so it's just a flame in the open space. So we use quite a lot of the mesh, which might not be that efficient, but later on you will see that this type of simulation really not that costly. So we did a grids and domain independent study. Finally, we pick up this grids. So basically, you can think just we use the 1 millimeter cube as the smallest, a uniform computational cell. It turns out the computational prediction of the frequency scaling law is quite good. You can see that we check different liquid field, and also we change the gravitational constant. Okay, it's all follow this the square root scaling law. So now we recognize that probably the liquid pool is not that crucial, and then we can use some diffusion flames more commonly seen in our laboratory. Then we again for the reason of a comparison with our previous simulation, we changed the computation to gaseous field. So we use massing, for example, and then now the same setup. And now since you know that in the liquid pool case, the fuel supply is due to the heat feedback, and then to vaporize the liquid pool into a gaseous species. But here we use a gaseous fuel, then that means we need to give some initial the inlet velocity to supply the fuel. Then the question is, does the inlet velocity U0 affect our study or not? So you can see that overall the scaling law is still very good, and then we change the initial velocity of the jet. So you can see that within the error bar, the frequency doesn't change much. So then we just pick up one of them. It's in the following simulation. So then you might ask me, what kind of chemistry you used in your simulation? And then, so because at that time I recognized that this is a diffusion flame being far away from local extinction or regulation. So we don't need to worry about the chemistry. So basically the reaction zone sheet, the reaction sheet approximation is enough. This is a standard procedure in studying diffusion flame. So then we can check that actually this is the case with a very large Dunkel number. So if we use the finite rate chemistry, for example, we use this one-step overall reaction mechanism for massing combustion, and then we can see that the reaction time scales is much smaller than the either buoyancy time scales or convection time scales. So you may ask me why now there are a lot of good detailed reaction mechanism you are still using one step. So it really doesn't matter. If you want, you can use a detailed reaction mechanism. You just waste your computational resource. Because in this case, when Danko number is much larger than 1, and then we don't need to worry about that. And for us, we try to minimize the computational effort because you know that the more reaction you include in the calculation, the more chemical reaction time scales you introduce to the problem. So basically that means you will have a number of Danko numbers, and then we don't need that kind of detailed study of the comparing the flow time scale with the reaction time scale. So basically, so here we just introduce one chemical reaction time scale. Now we have 3 reaction time scale here. So you can see that they will give us 2 dimensional parameters, which will be used to study the flame behavior and the different parameters. Okay, so then the question is, what about if we introduce some external disturbance? Because I said we treat the flame as oscillator. So this is a common study when you study the dynamics and then you oscillate, and then you have a forcing the disturbance or whatever to see how this oscillator responds to the external disturbance. So this is one reason of studying this. The other reason is probably some of you guys know me. A few years ago, I was kind of amazed by some study of a firewall. Okay, so the firewall is the diffusion flame and the external rotatory or swelling flows. So then I say, why don't we just study how this flickering flame responds to the external rotatory flow? So it turns out the combustion experimentalist, I believe this work is from USTC, Professor Lei and his group, and then they observed that it actually increased the external flow velocity, and then they can observe the frequency increase in a certain range. Okay, so then we study weakly rotatory flow. You will see that why I will choose weakly rotatory flow is because in this setup, we can maintain the good axis symmetry of the problem and then simplify the theoretical description. We can still get very beautiful theoretical result. Of course, later on, we increase the swirling velocity or rotation velocity, and then we get a normal flame behavior. So in terms of computation, still this setup, same domain, but now we have 4 window words. We use we add the tangential the flow velocity into the box, and then in this way, then they will create a rotational flow around the flame. So since the domain is big enough, so we don't need to worry about the boundary effect and then the corner effect. So you will see from here. So basically, in the following calculation, most of the cases we fix the angle of the tangential flow, and then we just change the flow velocity u. We define this as rotatory intensity. So basically, you can think the larger R means the stronger rotational intensity of the flow. So here, this is what I just try to emphasize, that within this setup, we maintain a very good axis symmetry. So you can see that we try to look at how the velocity change with radial coordinate in different directions. So they all coincide with each other, which indicates we have a pretty good axis symmetry. Actually, I mentioned that once there's an axis symmetry, and then the first term, the stretching term in the vorticity transport equation is gone. So then we only need to worry about that source term. Also, we found that the velocity distribution is very similar, not exactly similar to that of the Rankine vortex. So you can see this is the mutual velocity linearly change with the radius, and then the outside the vortex core, and then decrease inversely proportional to the radial direction coordinate outside the vortex core. So then what we observed is exactly the same as experiment that increase the rotatory intensity, the flickering frequency increase. So you can see that for this non-swirling case, no rotational flow, the flame will start flickering. I mean, the vortex shedding occurs at the non-dimensional time 0.9, but here occurs earlier. Even though it looks like this vortex shedding occurs at the far downstream, but actually that puzzled us for some days. And then we recognize that once you introduce external flows, actually this external flows will introduce additional vertical flow, which will push the vortex to the downstream faster. Okay, so even though the flame flick faster in this case, but this vortex shedding occurs at the far downstream. So the results show here, we try different ways to determine the frequency, and then it turns out they all agree with very well and with negligible errors. So then the normalized frequency change with this rotational intensity in this non-linear way. Okay, this is not exactly, there's no reason we can think this is linear. So that inspired us to look for the theoretical interpretation. So let's look at the vorticity equations again. As I said, since the flow has a good axis symmetry, so we don't need to worry about this term. It's 0, and the incompressibility makes this is 0. It's single flame, so we don't need to worry about diffusion because there's no diffuse the vorticity into the flame. So then that means besides the buoyancy term, there's only one term we ignored in our previous theoretical investigation. So then we try to look at whether this is really important in this case. Then we look at the pressure gradient. We found actually it's a substantial pressure gradient caused by the external rotational flow. So then we decided to include this term in our theory. But then the derivation of the theory is pretty much the same as the previous one, with one major difference is that we include one more term, the baroclinic term in the theory. So I will skip the details and then directly tell you that we can again get a very nice the scaling relation. So you can see that this is just a Stoker number, non-dimensional frequency. And then the difference is then we have one more non-dimensional parameters due to the external flow, the rotatory flow. And then we found that actually the difference of the frequency with external flow minus the frequency without the external flow change linearly with R squared. Okay, it's very good the scaling relation. Then we recognize that that's of course because if everything's caused by the buoyancy, I'm sorry, the the barokinetic effect. Barokinetic effect is the pressure, and the pressure is related to U square, and the U square is related to R square. So that's not surprise to see this scaling law involve this R square. So is indeed nonlinear. So I think I should make things faster. And then let's just quickly show you if we increase the rotational velocity, we study how the flame behaves in strong rotation, rotatory flows. There are some previous experiments showing a lot of interesting behavior of the flame. So we try to computationally reproduce them. And then we recognize that since we introduce a strong rotatory flow, and then we have to be more careful with making the large Dunkel number assumptions, because the flow characteristic time might be as small as the chemical reaction time. Okay. So again, here we have only one Dunkel number, because I use a one-step overall reaction here. Then we use the finite rate chemistry, and then we reproduce the result and find out the finite chemistry reproduce very good the scaling law. So then we can try to reproduce all this flame behavior. Because now by increasing the rotational velocity, the flame might not be flick anymore. So the frequency is not a good indicator of flame behavior anymore. So then again, I still think this is something about a flame oscillator. So I would adopt it a dynamics, nonlinear dynamics approach to study this problem. I will show you very quickly. So you can see that with increasing R, the rotatory intensity, we reproduce the flickering, faster flickering, oscillation flame, steady flame, lifted flame, and then the spiral flame, and even the flame with a vortex breakdown. I will show you very soon. I just give you some computational result without much interpretation. So you can see that I choose 6 points along the vertical directions. I will show how this point, the velocity of each point in this 3-dimensional phase space, I will show the 3 velocity here in this lower phase space, because this is based on the understanding that we are interested in the dynamic behavior of the flame, not the details. So even though when you do the simulation or the experiment, there's some external disturbance, that will change the flow details, the flame details, but not change the topological behavior or shape of the flame in phase space. So you might ask me why you change 6 point or 3 point in each phase space. It's because we are living in a 3-dimensional space. This is the best we can do in terms of visualization, right? So, but this problem can be generalized into any dimension of phase space. So basically here, what we call is dimension reduction. We change infinite dimension of the problem, which controlled by PDE into finite dimension problem controlled by ODE. So if we run the simulation for sufficient long time, what we will get is just not a phase curve, and it's a phase portrait. So you will see a lot of different shape of the phase portrait according to different dynamic behavior. So this is a flickering case. Sorry for this typo. Flickering case, and then you can see a closed loop. That means there's a periodical the motion. Similarly, the upstream is periodical. Now, faster flickering, we have both periodical motion downstream and upstream. So if the flame is oscillation, that happens, the vortex shading occurs downstream of the flame. So there's no chance for the vortex to nag the flame to make the flame to pinch off. So that's why we can only see the periodical the motion in downstream, and which only slightly affect the flame, so make the flame oscillate instead of the flicker. So upstream, you can see there's no clear the periodical motion. So if we further increase the rotational intensity, so you can see that the vortex shading occurs much further downstream, and then the upstream flame maintains a steady state. You can also see there's a totally different phase portrait in the phase space. So this is a lifted flame. As I said, this is the one of the consequences we introduce the finite rate chemistry. If we keep using infinitely fast chemical reaction modeling, there's no way we can reproduce this. This is well known to our community. So I will skip this. So basically, we contribute all the phenomena into the position and then the rate of vortex shading. And then if we change the angle of the external rotatory flow, and then we can reproduce the spiral flame. Actually, the spiral flame, we are still studying that, but we believe that this is due to some symmetry breaking. So the flow cannot maintain the axis symmetry, and then it's because the symmetry breaking, and then the flame will behaves in a spiral. So this is a vortex breakdown case, and actually we got this result long time ago. At that time, we were quite interested in what some of our colleagues in this community discovered, the blue world. So at the beginning, I recognized that to recognize to computationally reproduce a blue world, the first step, we must introduce finite rate of chemistry, and then due to the lift off, and then the flame is, once the flame is lifted off, there's a chance for the fuel and oxidizer to mix in the upstream, and then to form the premix flame structure. So I believe that a couple of years ago, they already published something, but we never got the chance to publish our result because we didn't got a very good, beautiful theoretical interpretation to what's going on here. Okay, so now we move on to two flickering flames. So it's just like we have a two flame oscillator, okay? And if they are far away from each other, you can see they will flick independently in a phase difference of pi. If they're close enough, they will flick in the same phase, okay? The phase difference is 0. So you further increase them, they will merge. Of course, that's not interesting. So to understand this, again, we use a computational methodology. You can see that here we go back to the heptane is because originally we started from heptane. So this work we did this work first, and then move on to gaseous phase, to gaseous fuel. So we validate everything, the single flame, and then we produce two identical flame with a certain separation of distance. And then you can see that with certain separation, we reproduce the antiphase flickering. So we can see because here I show you the toroidal vortex, the vorticity. So you can see the one vortex can influence the other vortex. So, but they didn't have the chance to touch to each other. because they're far away from each other. So I believe this interaction between flames through the convection. And later on, we know that this is a vortex-induced flow at the location of another vortex. So this is an in-phase case, and then now the two vortices are close to each other. So there's a diffusion between this positive and negative vortex. So they cancel out. Once they cancel out, they merge to a big vortex, and then the big vortex will start this the shedding of motion caused the flame flickering. So then, right away, we recognize that this is a convection dominant when the flames are far away from each other sufficiently, and then it's a diffusion dominant when they're close. So the competition between them must be controlled by something like a Rayleigh's number, because we got this analogy from with the well-known the common vortex strait. Depends on Rayleigh's number, you can have this closed streamline configuration of the flow, or you have this is the open streamline configuration. You have a vortex shedding off from the cylinder periodically and then alternatively. So based on this understanding, we propose a criterion, because dimension analysis will give us only two non-dimensional parameters. Oh, sorry. If we just plot all the results in one-dimensional, one parameter alpha over D, we will get something like this. So if we multiply alpha and the Grashof number, square root of Grashof number together, we will unify all the results in this nice diagram. So this inspired us to say, okay, so this flow is controlled a lot separately by these two non-dimensional parameters. They combine together to influence the problem. And once we combine them together in this way, then naturally there's a Rayleigh's number is similar to Rayleigh's number coming out from the problem. Okay, finally, let me give me 10 more minutes if you are allowed to talk about the multi-flames. So for three flickering flames, actually Okamoto and L did an experiment several years ago by using candle flame. They observed a few distinct dynamic behaviors or modes. In phase, okay, partial in phase. Partial in phase means there's no phase difference for two flames, but there's a phase difference with the third one, pi. And then rotational means there's the 2 pi over 3 phase difference between each two flames. And then the death mode means that the flame looks like a steady flame. There's no flickering at all. So at that time, we didn't start doing the experiment. So we use simulation again, the same computational setup, and now we have three flames. And then successfully we reproduce all the interesting the phase mode, the dynamic behaviors. So I will quickly go through them. So first is the in-phase mode. Then we recognize the in-phase mode is due to the so-called the vorticity reconnection. Because we have three toroidal vortices, and then they will reconnect to each other to form this kind of trefoil vortex. So the flickering is due to the shedding of this trefoil vortex. And according to the previous theoretical study, we can decompose this the Laplacian of vorticity vectors into two parts. And then we don't need to worry about this part. This part we just stretch the vorticity line without breaking them. So if we look at this, then we can clearly see that there's a tendency of breaking the vortex line to form the vorticity reconnection. So now we will be able to explain this by using the vortex dynamics terminology. So the Flickering death mode is because the certain situation, the vortex shutting off is downstream of the flame, so there's no chance to pinch off the flame. So the only influence of this vortex shedding is just slightly affect the flame to make them to oscillate without the apparent flickering. This is an asymmetric mode, rotational mode. So again, this is the alternative, the shedding of vortex. Now there's no vorticity reconnection at all. So the interaction between each flame is through the vortex-induced flow. So how to quantify this vortex-induced flow? And then recognizing that if the flow is asymmetric, the inner product or the dot product of velocity and the vorticity is absolutely zero. So the non-zero value of this term, we know that this is the holistic density, can used as a kind of indicator to show you how much the local flow is away from axis symmetric. And then this is a non-symmetry behavior. Of course, it's caused by the flow induced by other vortex. So finally, partial in phase is because there's two vortex reconnect with each other, and then they influence the third one through the vortex induced flow. So I will not come into the details anymore. So with all this, then of course, this is a computational combustion similar, but allow me to say something about the experiment, because we recognize that once we have 3 flames, we have a far more complicated dynamic behavior than what we just showed by using computational approach. So we did the experiment and we did observe that there's very complicated dynamic behavior. It's too complicated to make judgment by our eyes. So then we recognize that for dynamic behavior recognition, we need to invent some novel, some totally different the ways to do that. So our approach is to first try to get some flame features. This can be the flame height, flame width, the brightness, yeah, you name it. And then we use dimension reduction to pick up some characteristic quantities. So up to you, you can pick up 1 or 2 or even more. So for us, at the beginning, we just pick up 1 characteristic quantities for each flame. Then we can form a phase point in a 3-dimensional phase space. So then, because we can run the experiment as long as we want, so we can have a much more phase point in this phase diagram. So we can form this kind of the force portrait. Okay, it's difficult to make any observation, so we project this phase portrait into 3 2-dimensional phase space. So then we can get this kind of the diagram. Okay, for different dynamic mode, we can have a quite different the phase portrait. So you can see that, and then we can use the methodology based on phase space to recognize some typical dynamic behaviors. But then we still have trouble because in experiment we observe a lot more dynamic behavior, which cannot or very difficult to make a judgment with this behavior belongs to any of this the mode. So then we must develop some objective ways to do things instead of use subjective way. So then, inspired by some the recent development in the machine learning, I learned the terminology. It's called Wasserstein distance. This distance is the distance between two probability distributions. Okay, so we can talk about how far this Gaussian distribution from this Gaussian distribution, or even from this gamma distribution. So we can talk about the distance between distribution. Now we forget about the topological or shape or whatever of the phase portrait. We just treat them as a certain distribution in phase space. Then we can just calculate, okay, how far, what's the distance between this butterfly distribution from this whatever distribution. Okay, we can calculate them. Then we have a quantitative description of the difference between different dynamic modes. So it turned out this methodology works very well, and the similar modes always have a small Wasserstein distance. So that means later on we don't need to use our eyes to judge which is which dynamic mode. We can just, based on this experimental images, and then to get the phase portrait, and then to calculate the Wasserstein distance, we know which mode they belong to. So based on this approach, we got this regime diagram. I will not talk about them in detail because you can see that there's a lot more the dynamic modes here. But it's one dynamic mode, or we shouldn't say call it a mode, because it's the untypical way, which means we don't have the fixed mode during a certain experimental run. Okay, which means if I set up parameters, we do the experiment during the whole experiment, and then we can see the flame for some time behaves like this mode, then change to another mode, and then they change back. So we have this kind of untypical mixed mode. So this is challenging the problem, and then by coincidence, we found that actually this paper and published by a bunch of guys working in machine learning areas, they cited our ICAF manuscript of this paper, and then they actually thought much more than us, and then they are dealing with the so-called untypical modes, because here they try to, based on some the accelerometry data, to recognize the human motion. So you can see whether a guy is walking or running or jumping or whatever. So it's different from what now popular, the image recognition or image classification. This belongs to what I said. It's called motion recognition or movie recognition. That means I don't care what does this flame look like, whether this turbulent flame or laminar flame, whether this flame is in a very good condition or there's a lot of disturbance there. But what we try to determine or recognize is the dynamic behavior, is what the flame is doing, okay, instead of what the flame looks like. So we are working on that, and we are making a very interesting progress here. Okay, so I think probably I will quickly conclude my talk here, because the rest of this, the result is just extend what we have now to include more flames, and the more flames means more practical in some sense, and more complicated in the other sense. For example, if we have a circular array of flame, and you know there's a very important configuration to place flames in a circular array. And I believe in our community, and there are people doing that, especially in recent years. I noticed that Hong Kong UST, the Professor Larry Lee and his group and his collaborators are working on this circular can combustor, the instability, thermoacoustic instability. It seems like they are studying the similar dynamic behavior, but in the context of turbulent flames. Okay, so I think I don't need to repeat what I just said, and then just stop here, and then I'm happy to answer some questions.
Okay, thank you very much, Professor Zhang, for your very interesting talk. And in the following, we will have the Q&A session. Okay. Yeah, so we have the questions from the audience. So the first question is, thank you, Professor Zhang, for the wonderful talk. And could you explain how the elevated pressure affects flame flickering? Yeah.
That's an interesting question, and I didn't go to the details. So if we go back to the beginning of the PPT, let me go back to that to see what are the factors influence the frequency. You will see that the flame temperature. Okay, so I think the pressure will change will influence flame temperature, and then also here. This term. This is the ambient density divided by the density of the flame. Okay, so you can also, if we make assumption of the isobaric assumption, the pressure is constant. So basically, this is a flame temperature divided by the ambient temperature. Okay, so apparently, you change the pressure, you will change this factor. Okay, so it's a substantial change. Look at here.
Okay.
It's the ratio -1 and then the square root. So you can see that you change the pressure. For example, if you drop or you increase or reduce the temperature by 200, 300 K. Okay, so you slightly change this ratio because this is the ratio of the flame temperature to the ambient temperature, right? And then you take the square root. Then you can see that this, as long as we still have the flickering, and then you will slightly change the frequency. Okay, but of course at a certain time, you will suppress the frequency. Okay, that's a different story.
Okay. Yeah. Okay. Thanks. Then any questions from the panelists? So for the panelists, if you have any questions, you can unmute yourself and ask directly. Okay. Thanks. Yeah. So maybe I'll ask the second one. So here you mentioned the single flame, right, and also double flame, right? Then identify different modes from there. So is there any actual relation between the single flame and also the double flame, or even more because you talk about the collective behaviors of multiple flame?
The difference you mean is the difference in terms of frequency or what?
Mode and also the frequency.
Oh, so okay. First of all, if we have more multi flames, the frequency is not good. I shouldn't say it's not good. It's not the only way. It's not the adequate way to study them. Okay. Right. Okay. So you may have a number of the oscillation mode, right? So you have multiple frequencies, Now we don't have this one single frequency to talk about. So you can see that if there's two flames, apparently we can have the in-phase anti-phase mode. That means the two flames, due to the interaction, they can behave exactly the same, or they behave the same but with phase difference.
Okay.
Right. Look at this. Okay.
Yeah.
So if you ask me, what's the big deal with that? So I can tell you, and it's maybe not two if it's multi-flames and a different dynamic mode that will have a very different the oscillation or acoustic behavior. Once we are not talking about flame in open space, if we have a confinement, okay, so you can see that different mode will have a different, will cause different thermoacoustic instability. I assume. So later on, probably I will start doing this study by introduce the confinement, just like other people is doing now.
Okay. Yeah, and then because finally you're talking about the multiple flame, right?
Yeah.
So in this case, how to generalize the conclusions like from double flame or even triple flame and to more flame numbers? How to generalize, or is it possible to generalize, or it is very difficult?
Originally, we saw it's difficult until we developed this so-called Wasserstein space-based on methodology. Because you can see when the one flame is oscillating and flickering, two flames, in phase, anti-phase, three flames, we can make the judgment of dynamic modes about our eyes, right? So if we have multi-flames, so you can expect that you will have a lot more dynamic behavior, which you cannot say much if you just use your eyes.
Yes, because it's more complicated,
More complicated. So I believe that in our community, in fluid mechanics community, they develop their own methodology adopted from the turbulence study, right? A turbulence is good. It's good. The battlefield for dealing with multiple scales, multiple modes, right?
Yes.
So similarly here, we adopt a different approach. So all the methodology I show here can be easily extended to higher dimensional space.
Okay.
Even when I have 20 flames, so each flame I pick up only one characteristic quantity. For example, the flame temperature or the flame velocity at a certain point of this flame. Then I form a phase diagram or phase portrait in a 20-dimensional phase space. Okay. You might think this is difficult to manage, but now no problem. We don't need to visualize them. We just know space point will form a force phase portrait. Different force portrait corresponds to different dynamic behavior. So how to characterize them? We just compare how far this portrait from that portrait. We just calculate the so-called Wasserstein distance. This is a quantitative description. It doesn't depend on our eyes. So this can be easily generalized. So that's why what we are doing now is just, for example, this flames in circular array. You can use the same approach, no problem. Now later on, you will not see this kind of a three-dimensional phase portrait because there's no way I can present to you any phase portrait in higher than 3 dimensions. So I just rely on this Wasserstein distance to tell you this behavior, dynamic behavior, is different from that one, even though it looks like very similar, but they are different.
Okay. Yeah. Okay. Yeah. Thanks. And for the application, you also mentioned the annular combustor, right? So for the annular combustor there, we have turbulence, we have turbulent flows. So what is your comments regarding the role of turbulence on the stability of these different fuel jets or different the fuel streams or air fuel streams from the burner, right? Yeah. For annular combustor, we may have different, probably we have tens of burners, right? And so what is your suggestion for the designers to evaluate or to calculate the distance between these different burners? So any insights from this work for the gas turbine designers and so on?
I understand. Very good question. And you see, I'm not an experimentalist, right? So I never work on any engine. So I noticed that there's some wonderful work, which I already mentioned, that Hong Kong USTC, Professor Larry Lee and his group, something like that. So they use a quite complicated, of course, the well-recognized the approach to extract the information from turbulence influence the flow.
Okay.
You see, the problem is it depends on. I think it depends on the dynamic mode, the frequency of the dynamic mode. It's close to, for example, turbulence is full of eddies with different time scales. Right? So if the dynamic mode, the time scale of the dynamic mode, it can be decoupled from those turbulent small eddies.
Okay.
So just like when we do the LES, we do the filtering, right? So we filter those small eddies, small time scales. Then what we get is the collective behavior of those time scales close to each other. My approach is to provide a methodology to help us to extract some information like that.
Okay.
Okay. For example, even turbulence flame, I can still do the same thing. I believe so. I place sensors at the different locations. I know those sensors will give us the velocity fluctuations, right?
Yeah.
When we present all this fluctuating velocity in a phase space, I believe that would be very complicated, the phase portrait. But I believe that the fluctuation due to turbulence can be filtered from those low frequency, the global behavior, the overall behavior of this, the collective behavior. So what I'm saying is, of course, this is my hypothesis. Even in the turbulent flow flame situation, we can still do the same thing. We just try to separate what belongs to turbulence and what belongs to the collective behavior of multiple flames. I believe there's some intrinsic behavior due to the interaction between each other, not due to the individual eddies or turbulent fluctuations. I hope. I wish I explained your questions, but I don't have the suggestion or opinion toward any practical applications.
Okay. Yeah. No problem. Yeah. Okay. Yeah. Thanks. And my last question is, because here we are talking about the flame, right? So how about this flickering behavior in thermal plumes? So we will still observe this or no?
I think so. I think we can observe similar thing. If I remember correctly, and I met a guy, a professor. Now he's sorry, I forgot his name.
Because if it is the plume,
he was in Singapore, the Nanyang Technology University. Now he's in Sichuan University. I remember he did exactly the opposite problem as me, because my problem is a buoyancy control. His is a jet control, is a convection control. And then
Okay.
you can still see this kind of the behavior.
Okay.
So to answer your question directly, I believe we can observe something in the thermal plumb.
Okay. Because in thermal plumb, we don't have any chemistry there. We don't have any reactions, right? But the density ratio is there, right?
Yes. So actually, so that's why I apologize to my audience at the beginning of this talk. So if you understand what I'm talking about in this presentation, you will know that what I'm really talking about is the fluid mechanical problem, not the combustion problem at all. Even though it disguised by chemistry modeling, combustion, heat release, but you see the controlling mechanism is the vortex evolution and the interval.
Yeah. But combustion is a combination of fluid mechanics and chemistry, right?
So
yeah.
So you see, that's why I know some combustion, but I still prefer using the cheapest and then the easiest way to simulate things. Okay. I love to join you guys the OpenFOAM community, and then actually my current project requires using OpenFOAM. I'm doing the spring combustion problem.
Okay, spray combustion, right?
Spray.
Yeah. Spray. Okay. Yeah. So we look forward to your new results.
Sure.
Yeah. Okay. So any questions from the panelists and also the audience? Yeah. So if you have questions, you can submit in chat or you unmute yourself and ask. Yeah. Okay, so seems no more questions. Yeah, I think if you have any questions regarding this very interesting work from Professor Zhang, I think you can also write the email to him to have a direct discussion, right, after the talk, right? Yeah. Okay. Yeah. So if no more questions, let's thank Professor Peng Zhang again. Okay, so thank you very much for the very interesting talk. Okay, hope to see you soon.
See you soon. Bye bye.
Yeah. Okay. Thank you. Bye bye. Thank you. Bye.